Welcome everyone. This is the Drone Systems and Controls course. I am Vignesh. I am a teaching assistant for this course, and in today's lecture we are going to be taking a look at some examples of state transition matrices, similarity transformations, controllability and observability. All these concepts have been covered in the lectures, and this lecture is supposed to serve as a tutorial to give a more hands-on experience and a more mathematical example of all these concepts. In today's lecture, we are going to understand how to perform similarity transformations, how to calculate state transition matrices, check the controllability of a system, and check the observability of a system. First, we will start with some concept recap and then get into the examples. First, let's talk about similarity transformation by diagonalization. Now, let's consider the linear time invariant system. X dot equals ax plus bu and y equals cx plus du. We are going to do something called as a transform, and we define this transform by a transformation matrix P, and the transform is defined to be x equals pz. We are going to substitute pz in place of x. When we do that, if we take the derivative of x equals pz, x equals pz, since this is a linear system, what we will get is x dot equal to p times z dot. So we end up with this equation pz dot equals apz plus bu, and if we pre-multiply the entire equation by p inverse on both sides, now we will get p inverse pz dot equal to p inverse a p z plus p inverse bu, and p inverse p is nothing but the identity matrix. So we end up with z dot equal to p inverse a p z plus p inverse bu, and the output equation, if we substitute x equal to pz, it just becomes y equals cpz plus du. Now one important thing to note here is, when we were converting from standard or some state space form, some state space to canonical form, the state variables remained the same. However, when we do similarity transformation, the state variables themselves change, because now the new state variables are z. So just keep that in mind. And now if the state matrix A is in the controllable canonical form, then the matrix P, which is our transformation, diagonalizes A. So what does that mean? It means if we consider a matrix P like this, and note, just a very important note, this matrix P will only work if A is in the controllable canonical form and these lambdas are the eigenvalues. So if our P matrix is of this shape, which is n cross n dimension, then P inverse AP has the property that it is a diagonal matrix with its diagonal elements all being the eigenvalues of A. So where lambda 1 until lambda n are n distinct eigenvalues of A. So how is it useful? Where is it being used in drones? Similarity transformations are extremely useful when we are designing controllers, when we are designing observers, when understanding decoupling dynamics, and especially in model reduction. So in controller design, similarity transformation can be used when we have a controllable canonical form of the system A matrix or a diagonal form for easier controller synthesis. Controller design basically means we want to design a controller to control our system, and similarity transformation helps a lot in that. And it also helps in designing observers like the Leuenberger observer or Kalman filter. These are just state estimators, and it helps, similarity transformation helps in simplifying the system matrices. Simplification happens in the form of, if you remember, simplification happens in the form of getting a diagonal matrix as your state matrix. Look at this, P inverse AP is a diagonal matrix, and if we notice here, our new state matrix will be a diagonal matrix, and this helps simplify a lot of calculations. And now the next thing is decoupling dynamics. Similarity transformation can help in isolating different motion modes, for example pitch, roll, yaw, because of the diagonalization that happens. And lastly, if we have some complex drone dynamics, similarity transformation can help simplify that dynamics. And another concept we took a look at during the lectures was the solution to the state equation. Let's say we have a system which is defined by x dot equals ax plus bu, and now if let's say xt is defined by this is the solution of the state equation, and now what do we do with it? If you notice, this has e power at. E power at, as we know, is the state transition matrix. The state transition matrix has some importance. It describes how the system is going to evolve over time, and it allows the prediction of future states. It is also useful in stability analysis, and it is key in controllability and observability tests. How is state transition matrix useful in drones? It is primarily used for calculating the solution to the state equation, which in turn is very useful in trajectory prediction, simulations, control design, and state estimation. Particularly in control design, it helps in time domain analysis and controller design in the state space. Now, when it comes to state estimation, it is used in Kalman filters to propagate uncertainty and state estimates over time. And this will in turn help us with every other prediction that follows it. Now let's look at the examples. The first example is going to be the quad rotor pitch subsystem, which we have seen time and again in our lectures. So this is our pitch subsystem. This is the transfer function. If we trim the model at motor RPM of 1050, this is from the reference earlier that we had used to get this pitch subsystem. We get the numbers, the coefficients, which in turn lead us to the transfer function on the right here. Now we are going to use this transfer function. We have used this, and we got our controllable canonical form. The controllable canonical form is a special form where we have ones here, and the last row is filled with the coefficients of the denominator of the transfer function. Note that these are single input, single output systems, and multi-input, multi-output state space models will have a different calculation altogether. Right now we are just only focusing on the single input, single output system. The B matrix is given by 0, 0, 1. The C matrix will have the numerator here, and since there is no A square or S term, these two terms are 0, and the D matrix is also 0. Now let's do similarity transformation on this matrix. We have the controllable canonical form A matrix. We find the eigenvalues. We've looked at how to find eigenvalues in one of the previous lectures. I recommend you to go refresh your memory if needed. We find the eigenvalues of the matrix to be 0, minus 0.71 and minus 15.5. Now let's calculate the matrix P. If you remember, the P matrix is of the form 1 lambda 1 lambda 1 squared, 1 lambda 2 squared, and 1 lambda 3 squared. This is how it will look like. This is the transformation matrix. This transformation matrix will not diagonalize A if A is not in the controllable canonical form. So we get our P. 1 lambda 1 is 0 and lambda 1 square is 0. Next we have 1 minus 0.71, the second eigenvalue, and lambda 2 squared, and then 1 minus 15.5 and lambda 3 squared, which is 15 minus 15 point squared. Now we find the inverse of the matrix, which is this P inverse matrix, and if we multiply P inverse AP, we will actually get a diagonal matrix, which we define it to be capital lambda. Now let's talk about the transformation. These are the equations that we saw previously. Now the transformed system, we are going to call it as z dot equals azz plus bzu, y equals czz plus dzu, where az equals P inverse AP, which we defined it to be capital lambda, pz is just P inverse P, cz is Cp, and dz is D. So now we calculate az equals P inverse AP, which is nothing but capital lambda, which we found earlier, and if we multiply P inverse with B, we get the BZ matrix, and similarly we get the CZ matrix by multiplying C and P, and DZ is equal to D, which is just 0. Now let's talk about the state transition matrix. We found a similarity transformation here. Now let's go to the state transition matrix. How are we going to use this similarity transformation? Note that P inverse AP is capital lambda. So if we multiply capital lambda, if we pre-multiply both equations by P, if we multiply P and post-multiply by P inverse, this is identity, this is identity. So we will have A equals P lambda P inverse, and that's what we have here. The state transition matrix right now is e power at, and there is a special property which says that if we exponentiate this, it's e power at equals P e power lambda t P inverse. So our e power lambda t equals e power 0t, e power minus 0.1 t, and e power minus 15.5 t, minus 15.5 t along the diagonals. Hence e power at is P times e power lambda t times P inverse, and we get this equation to be our state transition matrix. This state transition matrix is extremely important when it comes to calculating the solution of the equation. So at any time t, we can find the exact value of xt, but for that we need e power at, and we found that from the matrix A by diagonalizing it using a similarity transformation. Now let's talk about the controllability of the pitch subsystem. The controllability matrix C, as we know, is defined by this, which is just the columns of the controllability matrix are B, AB until a power n minus 1b, where A is a n by n square matrix. So this is our B matrix, this is A times B, this is A square times B, and we find that the C controllability matrix is of this form, and if we find the eigenvalues, we get minus 0.091, 0.0435 and 252.8066. And note that there are no eigenvalues which are equal to 0. All eigenvalues are not equal to 0, which means that the determinant, which is just the product of the eigenvalues, is also not equal to 0, which means the rank of the matrix is 3, which is a full rank matrix, and that in turn means that the system is controllable, because we know that if the controllability matrix is full rank, the system is controllable. Now let's take a look at the observability of the pitch subsystem, where we define the observability matrix O to be C, Ca, C a power n minus 1, which are the rows of the observability matrix, and if we substitute the values for C and A, which is C, Ca and Ca squared, this observability matrix will be a 3 by 3 matrix. We get this nice observability matrix which just has minus 1.989 on its diagonals, which just means that the eigenvalues of the observability matrix are just minus 1.989 3 times, and none of these are equal to 0, which means that the determinant of this observability matrix is not equal to 0, and this means that the observability matrix is indeed full rank, with the rank being 3, and that means that the system is observable. Let's take a look at the other subsystem, the yaw subsystem, which we have also been taking a look at for the past few lectures. This, if you recall, is the transfer function of the yaw subsystem, and we trim this system at a motor RPM of 1050 with these values, again taken from the reference research article we mentioned earlier in the lectures, and we get the transfer function to be 0.11s plus 0.031 over s square plus 15.55s plus 0.775. And now let's take a look at the controllable canonical form of this system, which is defined by xc dot t, ac xct plus bc ut y equals cc xct plus dc ut, and we know that this is the transfer function of the yaw subsystem, where so now the controllable canonical form of this form, where AC is given by 0, 1, minus 0.775 and minus 15.55. Similarly, C is 0.301 and 0.11, BC is 0 and 1, and DC is just 0. Let's do the similarity transformation now for the yaw subsystem. I highly recommend that you try this on your own, since this is a very simple 2x2 system. Do it on your own and then come back and rewatch the lecture, pause it now and rewatch the lecture to check whether the calculations are correct. Do everything like similarity transformation, find the state transition matrix, do the controllability test and do the observability test. So now let's proceed. We find the eigenvalues of A, which we find to be minus 0.05 and minus 15.5. So the matrix P here in this case would just be 1 lambda 1 1 lambda 2. Again I repeat, this transformation matrix P will only diagonalize A if A is in the controllable canonical form. So we've got the transformation matrix P. Now we find the P inverse, it's just matrix inverse, and we find it to be 1.0032, 0.0647, minus 0.0032 and minus 0.0647. And if we multiply P inverse A and P, we will actually get a diagonal matrix, which we again define it to be capital lambda. And the diagonal elements are just the eigenvalues of A, which is minus 0.05 and minus 15.5. Now this is the standard form of the transformation, where the transformation is defined by x equals pz and z are our new state variables. So z dot equals P inverse AP, which is nothing but the capital lambda that we found, and the new BZ matrix is nothing but P inverse B, the new C matrix is nothing but CP, and the DZ is just D. So AZ is capital lambda, which is minus 0.05 and minus 15.5 along the diagonal of a diagonal matrix. BZ is P inverse B, which is this matrix. CZ is 0.2955 and minus 1.404, which is the multiplication of the matrix C with the transformation P, and DZ is 0. So let's use this capital lambda that we found during the similarity transformation to get our state transition matrix. Now the state transition matrix, as we know, is defined by e power at, and as we had seen the property already, it's just nothing but P times e power lambda t times P inverse, and e power lambda t is given by a diagonal matrix which has the diagonal elements to be e power minus 0.05 t and e power minus 15.5 t. Now if we multiply P e power lambda t and P inverse, we will actually get the state transition matrix e power at, which is nothing but the equation, the final equation here. And this is necessary to calculate the solution to a state equation, the state equation of the yaw subsystem. And now let's do the controllability test for the yaw subsystem. Again, the controllability matrix is defined as this, where the columns are B, A, B until A power A minus 1, N minus 1 B, where A is the N by N state matrix. And note that the controllability matrix C will also be a N by N matrix for a single input, single output system. Substituting for A and B, we get the controllability matrix to be 0, 1, 1 minus 15.55. If we find the eigenvalues of C, we find them to be minus 15.61 and 0.064, and again note that no eigenvalue is equal to 0, and which means the determinant of A is also determinant of not A, sorry, matrix C, determinant of matrix C is also not equal to 0, which means the matrix C is full rank, which means the system is controllable. And Now let's take a look at the observability test. We have defined the observability matrix with its rows being C, CA until C a power n minus 1. We substitute the appropriate values for C and A. We get the observability matrix to be 0.031, 0.301, 0.11, minus 0.0853 and minus 1.4095. We find the eigenvalues to be 0.2955 and minus 1.404. Again, no eigenvalue is equal to 0, which means the matrix is not singular. It is full rank, with the rank being 2 in this case, and which means that the system is observable. Now let's summarize the things that we saw in this lecture. First, we took a look at similarity transformations, which switch a system from one state space representation to another. However, in this case the system state variables will change. And we also saw that if A is P lambda P inverse, then the state transition matrix has this property e power at equals P times e power lambda T P inverse, where lambda is a diagonal matrix with eigenvalues of A as its diagonal values. And then we used the property of the controllability matrix to do the controllability test, where if rank of controllability matrix C is full, then the system is controllable, and similarly if the rank of the observability matrix is full, then the system is observable. Also, for a single input system, the dimension of the controllability matrix is actually equal to the dimension of the state matrix, and for a single output system, the dimension of the observability matrix is equal to the dimension of the state matrix A. And these are some of the reading materials which you can refer to for further exercises, and I highly recommend you do so. Thank you.